working towards medical school. Today we'll be going over some more commonly asked questions at both the high school and college level in regards to chemistry. If you need some homework help or tutoring, you can always check out the links in the description below. And with that, we can now begin with the questions we have for this session. So, in this equation here, it starts off saying that two reactions with different activation energies, one does not equal EA2. We're just writing down the information we're given to be able to answer this question, but they have the same rate at room temperature, meaning that the K value, small k, equals K2 at room temperature. Okay, so we have two information right now, that the activation energies aren't the same, but the rate is the same at a certain temperature, which is room temperature. Which statement correctly describes the rates of these two reactions at the same higher temperature? So same higher temperature. So for this question here, it's actually more of a conceptual question. I would say honestly it is quite tricky, but you do need to use like the rate laws and everything to answer it, starting with this equation here involving the exponential factor. So I'm going to write down the full equation here. It's that the rate, okay, is equal to the exponential factor e, which is, e to the power of, so that's just a constant, but it's to the power of negative activation energy over R times T. And R is a gas constant in this case, and T will be temperature. But this is a formula that we're basing off that question. So now the reason why I say that it's conceptual is because you have to really break this down. So now, because E is being raised to a negative number, you kind of have to do the inverse in terms of relationships. So the two relationships you have to really focus on in this question is that because temperature is the denominator here, okay? So if temperature goes up, you're going to now have a smaller negative number, meaning that E will not be diminished so much. So in a sense, a higher temperature means a higher value for E, meaning that, according to the laws, when temperature is increased, which would make sense, the rate should also increase. So that's one of the things that we need to make sure we pay attention to. And the same thing can be applied for actually the activation energy. So because in the numerator, if you go through the steps I did, you'll be able to see that as activation energy increases, the rate will decrease. And it also makes sense because if you need more energy for the reaction to go through, then that means overall there'll be less of the reaction if you always need to be spending more energy. So that's why the rate would decrease. So with those, we need to make sure that we're looking at the whole picture here. The main thing being is that because this is happening on an, let me just get out of there. Because this is happening on an exponential level, okay, that means that these changes aren't in a linear fashion. So these changes will, if it was a graph, okay, it would look more like that, as in it's exponentially increasing. Well, in this case, because it's a negative, it'd look more like, it'd be a weird one, something like this. Overall though, it's just a really weird thing. Point being is that it's not a linear function. Okay, so now let's go into the question and try to break it down step by step, because that's the part that gets a little bit confusing. So now we have, if we put these two together, K1 is equal to K2 at room temperature. Okay, so let us write everything down that we have. So remember that A okay, this A right here is a constant. It's an exponential factor, right? But this exponential factor varies for every, molecule going through reaction. Any formula can have different exponential factors based on their surroundings and everything else, like how the concentration is and everything. You can actually calculate this based on the other information given, but right now we just know it's some number. So we're going to start labeling everything by 1s and 2s based on the two reactions, okay? So if we write it out, since the two K's are equal to each other, that means A1 E to the power of E activation energy 1 over R times temperature 1, okay? And temperature 1 is a room temperature in this case. Actually, so to make it less confusing, I'm going to put temperature room is equal to A2, okay, E activation energy of the second one over R times temperature room. Okay, so now we have those two. So these two equal the same thing, but these two numbers are different, the activation energy 1 and activation energy 2. The only place it can change really, since everything else is constant, because that's just a gas law, R is just a gas law, so we don't really need that. The only thing that can change is actually the exponential factor, okay? And if it equals the same, let's say now, because the question is asking, with the larger or the smaller activation energy, right? Let's say that EA1 instead doesn't equal, let's erase that, and let's say that EA1 was bigger than EA2. So activation energy of the first one is bigger than the second one. If this right here is bigger than the second one, okay, that means that E will be a smaller number, okay? Because remember, if activation energy increases, K decreases. So to make up for it, this A1 has to be a bigger number than A2 for it to end up equaling the same. So I hope you followed. So if overall the activation energy here is a bigger number, okay, than this one, so this is a smaller number, I'm gonna put it in red so you can at least track with the colors. That means that A2 has to be smaller than A1, okay, because this has to make up for the fact that it's a larger negative number. So that means with that logic here, okay, A1 is greater than A2, and that will always stay the same. Now, as I mentioned, this is an exponential difference, not linear. Okay? And the reason why that's important is because now we have a new addition to the information that A1 is greater than A2. So now the question is asking, what happens when you increase the temperature? So let's write it out again with the A1s and A2s, but different time and different temperature. A1 E activation energy of the first one over R temperature high. That's what we put here. And we have A2. We no longer know the relationship because, we've changed the temperature. A2 R temperature high. Okay? So now then, we have this information here. High temperature, increase in that, okay? Meaning that overall the temperature increases, the rate will increase. So remember, as temperature goes up, rate goes up. But how would it affect these two rates? So these two rates started off being the same at room temperature. And remember, everything is exponential. So when you increase this, right, you get overall in this section a smaller negative number still. Same thing for here, a smaller negative number, right? But remember the information that I told you, that the activation energy of the first one was bigger than the activation energy of the second one. So this smaller number here will be greatly affected by the change in temperature than this number. Because if the second activation energy was already small to begin with, it doesn't really get affected that much by a larger denominator. For example, if you had 3 over 10 versus 1 over 10, right? Okay, just as an example. But then you made it 3 over 100 versus 1 over 100. Still a huge difference, right? But this one went from 3 over 10 to 3 over 100. That versus 1 over 10 to 1 over 100, although it's the same, this is a linear aspect, the difference comes in is because you're now actually using it as an exponent. So this value here is no longer a linear comparison of 1-to-1 ratio. This change here is a much more significant change than this change here. Okay? And the reason why I wrote that just as an example, you can even be doing that in your calculator as well to even verify this information. That's why I say this is more of a conceptual question, because there are a lot of moving pieces, but you'll see that although the temperature is increasing in both scenarios, because in this case here, in the first case, since we had a larger numerator and then it's being diminished and then, you know, being exponented, you know, negative, this E overall will experience a drop, but not, will experience a major drop for sure. And same with this one as well. But then we see here that the A1 was bigger than A2. So although these two experience that drop, this E will still remain a greater number than that E. Hence the example that I showed here below. Okay, so that's 3 over 100, 1 over 100. So even though, yes, it is a negative, this number here versus that number, this would not have as much of a detrimental change, quote unquote, than this one, because of the fact that at the end of the day, you're going to end up with a smaller value overall for E. So both E drop. So I think what I'm trying to say as a summary for this question is that there is definitely a drop in the E. We can't really say by how much. We just know that the denominator increased. So the only thing that we can say is that because the A1 is greater than the A2, this will make up for that exponential change. And overall, this K value will actually end up being greater than K2. It's a very strange question. You have to make sure that you know your relationships for this one specifically. But yes, overall, you will see that the answer for this one would be A. That the reaction with the larger EA, so even though quote unquote larger activation energy does mean that the rate would be smaller, when you increase both temperatures and they start off at the same place, the one with the larger activation energy will reflect that change more. So that is A. And hopefully working through this, it just helps you understand that better. So overall, just know the relationships, and most importantly, once you get to the end, you'll see that although both temperatures increased, and that means that E dropped, because the exponential factor is greater than the second one, that's what makes it so that this one is able to have a larger K1 than the other one. Okay? So what they did here is just provided, you know, with numbers and such. So with that, as temperature increases, K increases. Yep. Both K's will double, but the higher activation energy species will still have a larger concentration. So that's how it works. So in terms of this relationship here, if you need to take notes, I'll just leave it on this screen. You can pause and just write that down. But overall, just know that relationship there, so that way you can answer these type of questions. So this is correct. And now let's move on to the next question. Okay, so in the next question here, it will just be simply classifying each molecule as an aldehyde, ketone, or neither. So with that, let's just get a head start here and just make our tables. So we have aldehyde and ketones and a neither group. Okay, so 3 groups here, and now let's actually write down what we know about these 3 groups. Well, the neither, we won't have to really write anything, but for aldehydes, actually, one of the ways they give away is the name. The name usually for aldehydes ends in Al if it's a primary group. That's how you classify an aldehyde. For ketones, the way they usually end is with ONE, okay? And neither, they don't end with either or. And the other thing about aldehydes is that the way they work is there's a functional group, okay? All right. And then it's attached to the carbon, but the carbon is attached to an oxygen and a hydrogen at the end. This right here is an aldehyde. So just move that a little bit lower for you to see. So this is an aldehyde group. It has that functional group, carbon, and the hydrogen. Now ketone looks very similar to that, but instead of it being a hydrogen, you'll see that it's just another functional group. So ketones is when the double bonded oxygen is just in the middle of the functional group, quote unquote, while the aldehyde, it's actually in the end because you see the hydrogen there. Okay, so now knowing that, let's go forward and answer these questions. So let's start with the first one, hexanol. Right away, you see the name ends with Al, so hexanol is an aldehyde. Okay, ethanol, same thing, Al, aldehyde. So very handy to just write down what you know about it. That way you get familiar with it. 2-methyl-1-butanol, also an aldehyde, if you guessed it, because same thing. Okay, so right now we have 3 aldehydes. Let's just go through the names first, because I do feel like that one's a little bit easier to grasp, because it kind of just tells you the answer right in its name. Propanone, another example of, well, not actually, not another, but another example of using its name, ends with ONE, so that would be a ketone right there. And heptanone, well, 3-heptanone, same thing, ends with an ONE. All right, so we have that. And methyl hexanoate, that one doesn't end with an Al or ONE, so we can put that safely in neither. Fun fact, actually, when it ends with an OATE, that's actually an ester, so definitely doesn't fit with an aldehyde or a ketone. And methyl propanoate, same thing. Okay, and pentanoic acid, that one, it says right there in its name, it's actually a carboxylic acid, so it's neither as well. Okay, and now let's go over to the formulas. So we see F bonded CHO. So let's just draw it out and then move it to the right place. Okay, so really it's a fluorine, a benzene ring, better benzene ring. Okay, and right here CHO. The only way for this to be bonded to CHO would be CHO, yes, but C still needs that 4 bonds, and oxygen does have 6, so it needs 2 more, just like 2 bonds for like to fill this space. So that's why we have a double bond here. So with that being known, if this is what we're given, okay, this right here tells us this is an aldehyde, functional group with the fluorine and the benzene ring, then it ends with double bonded C and an H at the end. So this right here is an aldehyde. Okay, and now we have CH3, CH2, 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 CHO. You see right away there is a double bond and it's on the last C carbon, so you can kind of tell that it's going to be an aldehyde. But this formula will kind of look something like this. So there's 1, 2, 3, 4, 5. So kind of like this: 2, 3, 4. Okay, And on the last one, it would be 1, 2, 3 carbon. Yep. And then it'll be like an H here, and then this will be double bonded to oxygen. So this is what that formula would look like. So that right there is the same thing over there, and that one is also an aldehyde. Let me just draw a nice line through it. Okay. If we go over to the next one, that one, if we draw it, we get something like this: 1, 2, 3, and the oxygen is down here. But you see that there's the carbon right after it. This right here, this will count as a ketone, because not followed by hydrogen, it's followed by oxygen. Okay, so just like our picture shows, 2 functional groups on each side, that's a ketone. All right, and then if we did the same thing, so that one looks like 1, 2, 3, 4, 5 carbons. So what I usually do is, draw, quote unquote 4 lines out of it, because this is 1, 2, 3, 4, 5. This is just how I'm drawing my carbons. Okay, and we see that the oxygen is on the 4th carbon, so something like here, and that one is also going to be a ketone. Okay, and then we have the last 3 here. We have something that looks like this. Okay, that one's just an alcohol. In fact, this is going to be ethanol, because it's 2 carbons and an OH. So that one goes over in the neither group. And this one, whoops, better lines, because CH3, CH2, CH2OH, this one's just propanol, also an alcohol. And now for the last one, we have CH3, CH2, then there's an O, and then it keeps going on like that. And this one right here, because the O is right there, as you'll learn, this is actually what you call an ether. So a strange one, but no dice. It's neither an aldehyde or a ketone. So we've gone ahead and broken down all the 15 of them and where they belong, and that would be how you classify each of these molecules. So let's see how it was done. So with that, they seem to have tackled, interesting, only the ones that, well, they didn't put all of them, that's for sure. But it looks like they're on the right track. They did show that the aldehydes are those that have the functional group on one side and hydrogen on the other, so that's good. Ketone, they did show that there's 2 functional groups on either side, and neither, they just put everything else there. So that is correct. And so with that, let me just put correct but incomplete. They did have the right basis for this question, so I'll mark that as correct. So let's go on to the next one here. What are we looking at? So with this, we have quite an interesting question, to say the least. This is talking about energy diagrams. Just make sure I have the right paper. There we go. So this question is a little bit of chemistry, a little bit of physics, but the point is that when an electron drops from one energy level to a lesser one, a wavelength is emitted. So let's actually go into the question. Let's just draw what we see, okay? So the energy diagram, it shows energy levels of an electron in a certain atom, okay? So just note that prefix, because zepto means 10 to the negative 21. It's important because you want to be able to keep your your numbers in the right place. So let's just kind of draw a mock version of it. I'm just going to draw the lines and just draw what each of the lines signifies based on the chart. So we have A, B, and C all the way up here. Okay, and A, if you squint really closely, all right, that's 150 zeptojoules. Okay, B is 2 lines above, so that's 250, and C would be 450. All of these are in zeptojoules. Okay, so we have that first part. Now the first question they ask is, what is the energy of the electron in the ground state? Ground state just means simply the least state. Okay, the least state the electron can be, not 0, but whichever line they give you that the lowest is. Okay, so that one would be A. So that means the energy of the electron at the ground state would just be 150 zeptojoules. So we have the first one done. What is the energy of the electron in the first excited state? It's just going to be 1 above the ground state. So that means for this question here, so part 2 would just be 250 zeptojoules, because that's the energy level of the electron in the next state above the ground state, because that would be the first excited state. And this is a ground. And this would, be the second excited state. Okay, so now if an electron makes the transition shown by the red arrow, so the red arrow is telling us it dropped down, okay, will the photon be absorbed or emitted? So the way this works is that for it to jump up an energy level, it needs to absorb energy. And I'm sure, as you can guess, if it drops down an energy level, it means it released an energy. It released energy to be able to go to a less excited state. So with that being known, another word for release would be emitted. So that means for 3, the photon would be emitted. So that would be for that one. Okay. And now let's go over to the fourth part that says calculate the wavelength of the photon that would be absorbed or emitted. We know it's being emitted, so we can just kind of start that. Okay. And it just says round to the 3 significant digits. So the way we solve for this here, you have to make sure we use the right formula. To find the wavelength, we need to use a formula, okay, that energy is equal to HF, okay? H being Planck's constant, and F just being frequency. And we know frequency is equal to speed of light, c, over the wavelength. And we are looking for, in this case, the wavelength. So let's do a little bit of modifying here, because in a sense we have energy is equal to hc over wavelength. So knowing that, we really just have wavelength is equal to hc over energy. So let's just plug in what we have. This is our numbers. We know Planck's constant is quite a big number. It's 6.626 times 10 to the negative 34, okay? And we know the speed of light is 3 times 10 to the 8th, okay? That's the speed of light. And we have here our quote-unquote energy. So the way we find that energy actually is because we have 450 to 250 zeptojoules, meaning that the difference is 200 zeptojoules, okay? I remember zeptojoules is 10 to the negative 21. So really we have 200 times 10 to the negative 21 joules. And we can kind of just plug that in there, okay? In fact, you can move these decimals here and you get 2 times 10 to the negative 19 joules. So we can put that down here. And we'll just go ahead. And don't worry, Planck's constant does have everything else you need in regards to, all the, right, I'm blanking out here. But the units, there we go. Yes, it has all the right units, and in the end, you should end up with meters. That's what you should end up with there. So you kind of just plug this into a calculator, okay? And you see that you get a value of 9.94 times 10 to the negative 7 meters. That is the wavelength, okay? But this question specifically asked for the question, this in nanometers. So nanometers is 10 to the negative 9, okay? That's nanometers. So if we move this 2 over, allowing us to not quote-unquote subtract 2 here, we have 994 times 10 to the negative 9 meters, which now this is allowed to be translated to 994 nanometers, okay? So that right there would be our wavelength of the photon that's emitted from this change. Let's see how they did, okay? Ground state 150, correct. So they got that part right. We also got the second part. That's good. Energy is indeed emitted. And let's see how they solved it. They got the 2 times 10 to the negative 19. Perfect. They used the formula to be able to solve for, well, they used the energy equals the Planck's constant times speed of light over the wavelength. And then they rearranged it, allowing to solve for wavelength. Although I do notice that what they didn't account for here is that 10 to the negative 7 gets to change to 10 to the negative 9. So this is incorrect, but only because nanometers is 10 to the minus 9. But it is pretty close though. But yeah, so quite a bulk of a question. But we're to get through that. That's why I mentioned this a little bit of physics in terms of just remembering your whole relationship between energy and wavelength and stuff. But the chemistry does mention that as well. So let's go on to the next question here. So, as our next question, we have lead thiocyanate, Pb SnC2, SCN2, has a KSP value. Okay, so I had to actually search this one up because there's a lot of weird values there, but it's actually 2.00 times 10 to the negative 5. Okay, that's what that's trying to say. That's what we have for lead thiocyanate. Part A is telling us to calculate molar solubility. So in a sense, how much in pure water would this dissolve? So remember the K value is pretty much saying how much dissociates and how much dissolves. So using that, we're just going to find a value that represents how much of lead thiocyanate solid when put into water would actually dissociate. And the way we do that is by using the formula known as this. So KSP is equal to, actually, before we even do that, let's just move this down here for some space. First, what we need to do is see what that lead thiocyanate breaks down into. So this is what the formula would look like. We have PbSCN2 solid, okay? And when quote unquote thrown in water, in pure water, okay, it's a equation that goes back and forth. We have Pb2 plus aqueous plus SC2SCN minus aqueous. Okay, so that means, remember that the KSP is the moles, moles per liter of product over moles per liter of reactants, but only if they're aqueous solutions, so we don't count the solids. So in a sense, what we really have here is Pb2 plus, okay, and SCN minus. Now you're probably wondering right away, how do we reflect the 2? When it comes to the K value, what happens, right, is that when you want to reflect that 2 in front of it, you square it. So this is going to be our KSP formula that we're going to be using. And here we also need an ICE table. So initial, change, and equilibrium. So we don't really know how much we started with, but in this case, it doesn't really matter because we're only focusing on the aqueous solutions being produced, because this is how we find our molar solubility. So we have that there's going to be, it starts off with 0, and the change is going to be plus x, same here, well actually plus 2x, because whenever this loses, so let's just say it's a value like a, because based on this form we don't need it. So initial is a for the PbSCN2, okay? So the way it translates, just use a different color. This matches up with there, this matches up with this, and this matches up with that. So for every 1 A loses, X gains 1, the Pb, and the SCN gains twice of that, based on this formula here. So we have just A minus X is a change. It's going to be X, and this is going to be 2X. Okay? So that means that really the KSP for this one here, if you just plug it in, it's going to be X times 2X squared. So KSP is equal to 4, because it's going to be squared, and instead of x squared, because it's an extra x, it'll be 4x cubed. So now let's just plug it in. That means that the 2.00 times 10 to the negative 5 is going to be divided by 4. Okay, that's going to give us, x cubed. So all of this is going to be cubed. I mean, the opposite of that. All right, so this is what we have here for that step, just so we're keeping along. Just going to move this over to the side. Okay, so that's what we have there. And we find out that when we do that, x is equal to, let me just double check here, the calculator, 1.71 times 10 to the negative 2 moles per liter. And this right here, this x value is going to be our molar solubility for this question. So it pretty much means for whatever value of A that's put in, that's how much is going to be produced in pure water. Now, they're asking us what happens now if it's not pure water. What happens if we actually have 0.900 moles per liter of KSCN. Now, fun fact, most things, in fact, if not all, when it's a solid that's with potassium, and especially in these questions where they don't mention that it has a K value, you can just assume they dissociate completely. So if we wrote down the formula, KSCN, it'd just be an arrow going one way, K plus, aqueous again, because this is solid, plus SCN minus aqueous. This is what it turns into. So if we know that we start off with 0.900 moles per liter of KSCN, it means that we have 0.900 moles per liter of K that's produced and 0.900 moles per liter of SCN minus. The only one that's important here, based on the formula above, the PbSCN2, you guessed it, would just be the thiocyanate, this part right here. So now if we go back to our ice table, it'll look relatively similar, but the difference is that our initial now will no longer be 0 for that part. So if we just put A again, 0 for the lead part, okay? And then here, instead of it being 0, it's going to be 0.900. And that's a huge amount in terms of the moles, okay? And the reason why I say that's a huge amount, because that is going to play into what we have to do with the later steps, okay? So the change here is going to be, again, plus x minus x, and here's 0.900 minus 2x, okay? And here again, this one is not relevant. We don't really need this part. This one's still going to be x. Now here is where it matters. You can see in our last question, what we really got here in this theoretical x was 0.0171. This is going against the 0.900, okay, theoretically. That doesn't stand a chance. Like the amount, whoops, it's not even going to be minus, it's going to be plus. Sorry about that. The amount that's going to be added to the 0.900 is almost going to be so insignificant that in the end, we're really just going to have 0.900 still. Because the fact that there's so much thiocyanate and because the K value is so low, it's not really going to change how much thiocyanate we end up with. And that right there is going to help us solve this question, because what we really have now in this question is the KSP is equal to x times 0.900 squared. Okay, so x in this case is just going to be the KSP over that 0.900 squared. And you'll find when you plug into the calculator, as you can see, the x produced is really small, 2.47 times 10 to the negative 5 moles per liter. And this right here would be the molar solubility when there's already some product there, in this case, in the thiocyanate. Now the rule of thumb, and most questions, if in fact not all, would have to do this, or else you would end up with a trigonometry type of equation, like something to the cubed, and you don't want to work with that. It's very frustrating. I tried it. When you have a starting amount that is more than 1,000 times bigger than your k value, in this case it's 2 to the negative 5, and this is really just 9 to the negative 1, that's already 1,000 times bigger. You can just kind of ignore it and say that the change here that we saw is negligible. Hence why we could go ahead and do this step here. Okay, so that would be the answer to that question here. Let's see how they did it. Okay, yep, 1.71 times 10 to the negative 2. Perfect. And here, yep, they did 2x 900, and then they actually did try to go with doing the cubic equation. Definitely have to show me how to do that. But overall, they should have gone exactly that. It would be 2.47 times 10 to the negative 5. But the key here, personally to me, is that the 0.900 doesn't change much, which is why you can just solve it like that, okay? Alright, now on to the next question. Hopefully everyone's having a lovely night right now. Now, let's see. The next question is, hopefully I didn't scroll too far. There we go. Which is expected to have the largest dispersion force? So largest dispersion force. Okay. So with that we have F2 fluorine, C3H8, C12H26, and BeCl2. Okay, so with this we kind of have to go over our rules for dispersion forces. First thing is that it's the weakest type of force compared to the dipole and hydrogen bonds and stuff. Okay, it's the weakest type, so it takes the least amount of priority. Everything else, if it could make it, like if it could be a dipole bond, it'd be that over the dispersion forces. Second thing is the larger and heavier means greater dispersion force. And the third thing, well, kind of ties into the second thing actually, would be that more surface area, okay, also would be an increase in dispersion forces. And the more polarizable, so not to the point to where it becomes a dipole, but when there's enough of a difference in electronegativity, that also favors T difference increases would lead to greater dispersion force, because it'll be kind of like a plus side attracting a negative side, hence why there'll be stronger dispersion forces trying to bring these two things together. But remember that this has a limit to where if it's too high electronegativity, this one becomes more of a dipole, no longer a dispersion force type of bond. Dipole. Okay, so now let's go over this. So we have F2, okay, two nonpolar things. In fact, let's go to our periodic table here. So that one we definitely know is a London dispersion force because it's competing with itself. There's no polarity there. This whole thing is going to be nonpolar. Okay. C3H8, we know that hydrocarbons are nonpolar, so we can also attach that to this one as well. Okay. Just write it in red so that we can keep track. So 3 of these are nonpolar. Now let's look at beryllium chloride. So beryllium is an alkali metal. So it's actually a metal and a non-metal And if you remember, that's an ionic bond. And ionic bond form dipole-dipole, as in there's definitely a positive side and a negative side. This right here is no longer a dispersion force. That one is out. So now let's base it on these three, and let's review what I wrote about each one. So larger and heavier and more surface area, greater dispersion force. Everything is nonpolar, so that electronegativity difference kind of just throw out. So we don't really need this part. Okay, so let's focus on just the first two, which is the largest and heaviest one and has the most surface area. That will be this behemoth here, which if you drew it out, looks something like this. 3, 4, 5, 6, 7, 8, 9, 10, 11. This is C12H26 versus C3H8, which would look like that, and F2 would just look like that. So this right here is our biggest one, and therefore this would have the largest dispersion force. So the answer is, well, the third choice, C. And now let's see how they did. Okay, and they did get it correct, and it did mention that barium chloride is ionic, so it's out. And then they also mentioned that because C12H26 is the largest one, that one is going to be our winner here. Okay. And now this question is asking us to calculate the value of Kp for the equation this. So we just wrote it out. It's going to look like carbon plus CO2 gas is equal to 2CO gas. We don't know the Kp, so there's the K for product, how much product is being produced here. But they do give us two formulas here. They give us carbon plus 2H2O turns into, well, just use that formula because there is a K value. Okay, CO2 gas plus 2H2 gas, and the Kp for this one is 3.53. So that definitely favors product being produced. Now the second one is H2 gas plus CO2 gas, okay, goes to H2O gas plus CO gas, and that would be Kp2 is equal to 0.699. So this one is kind of more reactant favored. So the way you solve for these questions actually is that you want to go through a process of multiplication, as in as you add equations, you're really multiplying them together. You're multiplying their K values, okay? But first we need to actually get to this equation here from these two given. So let's look at it. Okay, we have one carbon, okay, so that's good throughout the whole thing. So most likely this equation here is going to stay as 1. We don't want to touch it. Okay, so now we look at the other components. It says it only has one carbon dioxide. This one has a carbon dioxide here, but this one has a carbon dioxide here. At this rate, these two would cancel each other out, meaning that our overall reaction would have 0 carbon dioxide. And the last piece here is that there's CO gas, carbon monoxide. This one has only one carbon monoxide gas, and it needs 2 of them. And if you notice here, when you go through the rest of it, this right now would lead to 1 extra hydrogen gas being produced and 1 extra water in the reactants. So what I did here actually is that I noticed that by trying to not simplify but cancel each other out, I need to multiply everything here by 2. Okay, if I put a 2 in front of everything, you notice then that things start canceling each other out. 2H2, bam, gone, no longer in our final equation. 2H2O, also no longer in our final equation. 2 and 1, so this is going to be -1, and this one gets canceled out. So overall, when we put in our final equation, okay, we now have the same as the above, right? But what happens to the Kp value for this? Remember, when you add an equation, you multiply it. So what we've really done here is that we've squared it because we added the second one of it, so then we multiply it by itself. So now that Kp is going to be 0.699 squared. And don't forget the first equation we use is going to be multiplied by the 3.53. So I hope you're following, because first we balanced out the equation, and based on the fact that we had to use two of them, we multiplied this Kp by itself, hence how we got the squared, and then we multiplied by the first formula since we still have to add that one in. So overall, this is going to be our equation to find Kp. And when you plug that into a calculator, what you get at the end is that Kp is equal to 1.72. And that would be our Kp for today. Let's see how we did. So they have the equation, first one, second, and third one. And then first, what it is, they balanced it out. Interesting. It definitely did a very strange way. But what it did overall, because of the little signs here and there, it's hard to read. But what it did overall, I can see that they ended up with the same balanced equation of this, which is what we wanted. Okay? And they did say exactly, so Kp 3.53 times 0.699 squared. And that's how they got the 1.72. So this is indeed correct. And let's go over to the next question. Now this question here, luckily, it's almost a blessing in disguise to receive, because this one, as long as they give you a periodic table, you can always rely on it. Periodic table is your best friend. But this question is asking what isotope, okay, has 13 protons and 14 neutrons. Okay, so the way we solve for these questions, okay, it's an isotope. Easy way to remember it, and they do give you a hint actually of what it looks like. The answer is supposed to look like, you know, element and then their atomic mass next to it. That's what the answer will look like, supposedly. So we start like that. 13 protons, okay, that tells us our elements. So if we go to the periodic table, what has 13 protons, that will be aluminum. So right now we have aluminum, okay, but now it says 14 neutrons. A typical aluminum would have the same number of protons and neutrons, but because this one has 14 neutrons, what actually happens here, okay, is that we just add them together. That would be their quote-unquote not atomic mass, but how much the protons and neutrons when added together would equal. So in this case, 13 plus 14, we get 27. So this element here will be aluminum 27. That will be the isotope for this question. In fact, if you compare with that uranium example they gave us, uranium is 92. Okay, that is its number on the periodic table. So if we subtracted 92 from 234, you would actually see that means it had 142 neutrons. And you said these two would add up to 234. Okay, so that's how you'd solve these type of questions to get that. And let's see here. Yep, and they definitely got aluminum 27 because they first saw that the protons is 13, and that gives you your element, aluminum, and then they added it together. Alright, so that question served as a little breather as well, because we're on to now some more complicated stuff. So we have this question here. So there's a resonance structure for the peptide bond below that we want to be able to draw. So they give us this peptide bond here. So if I drew it out, it'd just be, as they wrote, H3N attached to a carbon. Okay, that's a carbon chain, and this attached to another carbon, which has an O up top. Okay, another nitrogen, hydrogen, carbon, and then COO minus. Okay, so this is what they've given us, and they say draw a resonance structure. Now, to draw resonance structures, what I like to do is actually like to draw it a little bit different way. I see a COO minus. What that means to me, the only way it can form is as carbon attached to two oxygens. Okay, it's not going to be carbon oxygen oxygen. This right here is wrong. Do not do that. So never put that. Okay, it's going to be carbon oxygen, and the other oxygen is also attached to it. But the big difference here is that one of them is going to be a double bond, and one of them is going to be a single bond. That's where the minus is. So minus means that, remember, they have an extra electron. That's why they're able to fill up like that. So instead of having to share again with carbon, which wouldn't be possible, it can kind of relax by itself because that's where the minus is. And now there's a reason why I did that, because resonance structures are structures to where the electrons are free-ish to move around that area. So now let's look at it through each part and see where it's actually possible for the electron to move about. So here, nitrogen literally has nothing to give, so there will be no resonance structure here that it can move. This oxygen, although it has double bonds and a single bond, this carbon really wants to keep that 4. Okay, so with that, there is really no space for the electrons to move. Carbon doesn't want to get 5, and carbon doesn't want to go down to 3. So there will be no resonance structure that can form here. Nitrogen, same thing, really wants that 3, doesn't want to double bond with anybody else right now, and even then, the carbons and the hydrogen and the other carbon can't even accept that double bond. So that's no. So then here is just another CH2 bond. The only place here that can do resonance structure would actually be this right here. How, you ask, is that we could literally draw this same thing, but instead this took the double bond and these two electrons moved over here, making this the new quote-unquote -1. Whoops. Making this a quote-unquote -1 now. And that is what they want as a resonance structure. So realistically speaking, we have drawn the first structure, but let me just draw out both of them, and then that way we have our answer. And then I'll draw an extra picture just to show how the electrons are moving in that place. So really, we have this okay, CH2 and COO. That is our first resonance structure. You can add in the electrons if you want and just keep consistent. I will, even though it does say you don't have to, but just that way you can kind of keep track a little bit easier. Okay, and then the same picture again, CH3 NH CH2 C. This one's going to be a single bond. Let me just draw a little bit better. Sticking out like that. And this one's going to be the double bond. So now the O is negative here. Okay. And this is what would signify our two resonance structures. Those are where the bonds are moving. Okay. And now, depending on how this, I don't know how that software works, but this is probably what is going to look like when they ask for that one resonance structure that would, I guess, represent these two together. Okay, is going to look like this. So same thing for everything else. Okay, and CH2. Now the way this is represented is that you still have these two lines to the oxygens, right? But it's going to be a dash. This is what represents the resonance structure, okay? And overall, you can just put the minus like right here, okay? Because this, just going to put it like right there to make it a little bit easier, because they're sharing that bond, okay? And there's an extra electron somewhere in that mess. So this is what's going to signify our resonance structure, and this is what the software is probably asking for you to draw. So with that, you're still going to have, just to make sure, 1 2 3 4, 1 2 3 4, but that quote-unquote 5 6 is going to be rolling between the two right there, just like that, because exactly if you take out that 2 and put it as a bond, it's quote-unquote there, but the carbon can only handle one at a time, so it's kind of always pushing, you know, that extra 2 electrons out, or yeah, in this case that's what it's doing. So this is what our resonance structure would look like in the end. So that is it for that question. Let's see how they did. Oh, well, there's nothing there, so I'm just gonna leave it here so you can pause as well, so that way you have an idea what you're looking for resonance structures. And just as a future note, when you do see carboxylic acids that have gone through like losing that proton, that oxygen, it's now that basic structure, but more importantly, that is now free to form a resonance structure, because now you've allowed it to now be able to move across. If there was still a hydrogen there, so for some reason if we still had COOH, now there's no way for the electrons to move. The hydrogen is taken up, but now the hydrogen is gone, it allows it to jump wherever and keep pushing things out. So that's how we get our resonance structure. Okay, all right, and now let's see here what we have next. So, which of the following is not part of Dalton's atomic theory? So this one's another one of those conceptual questions as well. All right, but the way I answered this one, when you read through it, in fact, I'll just write it down. Dalton's theory dealt with atoms as the smallest, I guess, yeah, the smallest particle. Yeah, there we go. And this right here is important, because now we know that's not true. We have protons, electrons, and neutrons. And then, you know, if you go into like some more of the quantum physics and stuff, they start talking about some other weird stuff. But point being is that now we know that the atom is no longer the smallest particle. But this is what Dalton based his theories on, that the atoms are the smallest particle. And now let's use that to answer these questions. Each element is composed of tiny indestructible particles called atoms. He did say that. That is one of his atomic theory. Atoms combine in simple whole number ratios to form compounds. So he kind of knew exactly that if you had two of one atom, like let's say 2 of chlorine and 1 calcium, so it's like a whole number ratios, 1 calcium, 2 chlorine. He did say that because they're still dealing with atoms at the smallest particle. It's kind of like baking mix and match. That's what he was thinking. All right, this just says all the above are part of the atomic theory. We can kind of skip that one and see if it's true. All atoms of a given element have the same mass and other properties that distinguish them from atoms of other elements. Okay, so now remember, he thought atoms were the smallest particles. He did not know about isotopes or anything, because he did not even know about neutrons and protons. So in this case, if you had just an atom, okay, of one element, excluding all the different forms of the isotopes it could possibly have, then yes, this is correct in that sense that, a hydrogen will never be the same as a helium, because these are two different elements. Same thing with calcium and chlorine. That is also correct. Now, E says most of the atom's mass and all of its positive charge is contained in a small core called the nucleus. There we go. That one is now beyond an atom. It gets even smaller. And Dalton never delved into that. He did in fact, he had the whole billiard ball model where he just thought that an atom was like that. And he signified like this is atom 2 and this is atom 3, something like that. Okay, that was his idea of what an atom was. He didn't know that there were different components to an atom. So with that, I'm going to keep that actually. So this is the billiard ball model. And now we know better that this is kind of like what we're dealing with now in terms of the newer models, the different shells of where electrons can be. And then, we have the nucleus in the middle. But this is not what he thought an atom was. So with that, the only answer here would be E, because E delves into a part that Dalton never thought about, which is that there are smaller things than an atom. Okay, so the answer here is E. And let's see. This person went ahead to state the whole Dalton atomic theory, and literally it is almost word for word, but there is one part that he does hide, that atoms are the smallest unit of matter that can take part in a chemical reaction. So he didn't think there was anything smaller. So by mentioning a nucleus, that should be a red flag right away. That's not the right answer, okay? So with that, I can confidently say that this is correct. And now, with this question, that will mark the end of my stream. If you need any more further explanation with the questions that we've gone over, definitely visit the link below. Great help. It allows you to just navigate through that. And honestly, I would say in regards to even the questions we went through today, there are many different concepts and things that you kind of have to go over and make sure you understand. So reach out for help if you're ever struggling. And with that, thank you again for joining my stream, and hope you have a wonderful rest of the evening.